We are now going to set up a system of equations, of linear equations, to solve this problem here as in an applied business problem. So let's spend a minute reading the problem here. But it says if 113 people attend a concert and tickets for adults cost $4, while tickets for children cost $2.25, and of course these tickets prices here are for each adult and for each child, and the total receipts for the concert was $383.75. How many of each went to the concert? And so after reading this problem and to align with our guidelines here, then the first thing is to identify the variables. And so here, among the people who attend the concerts, then there are adults and there are children. That's what we noticed through reading the problems. And ultimately at the end of the question right here, and usually it's a good practice to focus right at the ultimate final question of the problem, and that's usually is indicating how many variables are being asked for. So here in our question is asking how many of each, and each here we mean how many of adults and how many children went to the concert. So now clearly we have two variables. So now I'm going to name, so how about capital A being the variables to represent the number of adults, and really naming the variable here is just a choice right here. Anyone can make a different choice right here. And I'm going to use a letter C, capital letter C, to be the number of children. And so now at this point, and after we carefully check through the wording of the problem, we are sure that we're only going to have just two variables, and we already identified them all, and we have named them. So the next step now is to look through the entire information given in a problem, and of course there's no further need to read the final question anymore. But let's roll back and read the entire problem here as far as information to identify the relationships among the variables. And so we have two variables. So we are expecting two variables. And so according to the guideline, the rule of thumb, then two variable, ideally we should be looking for, we should be able to find two relationships. So that's something we're aiming at, even though, as I also said in the lecture, that this, even though being a rule of thumb, it's not didn't have to be a hard rule. There are still a few exceptions, but admittedly, most of the time, n variables, we're going to be able to find n relationships. So now if we look back a little more carefully at our very beginning statements right here and highlight that information that's saying if 113 people attend a concert. And so immediately reading this information, we must understand that these 113 people include children and of course adults. And so mathematically speaking, we now have found one relationship. And that relationship would be adults and children together, total of being 113. this is a relationship between the two variables. So we have found one of them. And let's look for another relationship. The problem says tickets for adults cost $4 each, of course, and for children it cost $2.25 each, of course, and furthermore, more importantly, total receipts for the concerts was $383. So total, this information here is important. Total receipts for the concert was $383.75. Meaning, with our whatever for the number of adults right here, at $4 each, we're looking at $4 multiplied with A adults together, added total up to, or added or total up together with the number of children at $2.25 each. This total comes out, according to the receipts, $383.75. So what we have found here is another relationship. And so as a quick check to ensure that we are under the correct guidelines, that two variables identified here, and we have found two relationships. So now we know that we are ready to go. And so what we have here is a system of equations. As a method to solve for this equation, we actually have three different methods available. We, or anybody, can solve this system by doing a substitution. This system of linear equation can also be solved by elimination. Or this same system can also be solved by, we can solve that system by using a matrix. And more precisely, an augmented matrix. And in case anybody choose to solve this system using an augmented matrix, then this is how the augmented matrix is going to look like. So right from the beginning, the equations also were written in a way where the variables are lined up in columns. So in the column corresponding to the A variable, then it looks like we have coefficient 1, and down at the bottom of the column we have a coefficient 4. So we now produce for ourselves the first column in the matrix is a 1, 4. Then in the next column over, the coefficient of the C variable here in the top equation is a 1. The coefficient of the C variable in the bottom equation, same column, is a 2.25. So now we have another column being 1 and 2.25. Here I put a vertical line. Some textbooks do this, or some textbooks do not, but vertical line here represents one column for the equal signs. And on the right hand side of each of these equations, these form another column for the matrix. So 113 and 383.75. But here what we have now is an augmented matrix. And this augmented matrix, once set up, it can be solved by doing row reductions by hand, or it can be done by inputting it into a calculator with the RREF function, and leave leave the solution for the OREF function to handle. I chose to use the OREF command from a standard TI-8384 calculator, which is also the tool being taught in this class. So the OREF command from a standard TI-8384 calculator reduced this augmented matrix into the following matrix: 1, 0, 74, 0, 1, 39. And once we're in the OREF row reduced echelon form of this final matrix, then remind yourself that this column is equivalent to the A variable, and this next column here is equivalent to the C variable. So from the top row over here of the reduced augmented matrix here, the way it reads now is that A, 1A plus 0C equals 74, or in other words, we now have found out that our A should equal 74. The next row here, what it reads now is 0A plus 1C equals 39. So here we concluded that C must equal 39. And this is how we have found our solution to the system of linear equations that we have set up previously. And it's always a good habit to check whether our found solution are truly the solution to the system, because sometimes we might have made a typo when we enter the matrix, or sometimes our solution by hand can also make mistakes. So checking the solution is always a good idea. So for now we found A equals 74, so I am substituting 74 into my first equation. And we found C equals 39, so add 39. We would like to ensure if the sum on the left hand side, and here I'm checking with my first equation, we would like to find out if the sum on the left hand side would equal 113 on the right hand side. And for now, I'll put check mark here because I haven't done any calculation equally on both sides yet. But so now, yes, calculation does turn out that the left hand side equals the right hand side. So our checking our two solutions that we found here, the solution for A and the value for C that we found, worked for this top equation. However, we still need to check for the next equation. So 4 times 74 plus 2.25 times 39. We have to also make sure that it's all equals to 383.75. And once again, for now, putting question marks there simply because I haven't done the calculation. And calculation does show that the left hand side and the right hand side in our second equation also satisfy equality. So now we can conclude that the number of adults attend this concert is 74, and the number of children attending this concert is 39. And that is our final solution. We have solved the system of linear equations.